Hello, everyone. It's me, Carolyn. Sorry for the tickle in my throat. Um, but I am fighting a cold, so just kind of bear with me through this video. In this video, we're going to be looking at another hypothesis test. This time, we're going to be looking at our proportion. Now, we talked about proportion before when we were looking at confidence intervals and things of that nature. So these things will show up again. So the same requirements that we had before will be needed as well. We will be using SALT again for steps 3 and 4 of our 5-step hypothesis test. But here we're going to be looking at proportions instead of means, and we'll see it. They'll read similarly, but a little bit different. So we're going to jump right into an example and kind of just this first step, just write our null and alternative hypothesis, which is step 1 of your hypothesis tests that we use. So we have the manufacturer of M&Ms claims that 40% of plain M&Ms are brown. So we took a sample of M&Ms will be used to determine if this proportion that are brown is different from what the manufacturer claims. So now here we see that we have this probability, and we also see the word proportion. So that tells me we're not talking about the average of something, we're talking about the proportion. So our hypotheses, your null and your alternative, will still start with our parameter of question. And in this case, our parameter of question is that proportion. So we put that P in there. And similarly to when we had the mean, we will start with an equal to symbol. And here we're kind of be equal to the value that is the status quo, or to be the assumed truth. And so that would be our 40%. However, we like to write proportions in their decimal form. So we're going to write that as a 0.4. Now we have the alternative is one that is either your less than symbol, your greater than symbol, or you're not equal to symbol based on the situation stated in the problem. So here we're thinking that it is different from. So different will imply that we are doing a not equal to, and again, that 0.4. If you want to write 0.40, so you see the 40%, feel free to do so. Now, to conduct those hypotheses tests, we will still go through the 5 steps. They'll be similar, but again, a little different, because after all, this is a little different situation. The first step, as it will be in all hypotheses tests, is to write those hypotheses. The second step is to choose the appropriate test and to verify any conditions that we have. In the case of a mean, we looked to see if we knew the population standard deviation or not, and also looked at the size of our sample. In the case of our proportion, what we had to check is making sure that our n times p0 and our n times 1 minus p0 that they're both bigger than 10. I want to remind you that n times p0 and n times 1 minus p0 is the number of successes. So these would be our successes, and these would be the number of our failures, or what we expect our number of successes and the expected number of failures. And if those do happen, then we will have a normal curve, and we will be able to find our test statistic. Our test statistic will look like this p hat, and we talked about p hat, and that is the sample proportion. That p0, which is going to be the value in our hypotheses, and then the square root of p0, 1 minus p0, and n. So very similar to what we saw in the confidence interval situation. Then we will use step 4, we will use to find our p-value. We also look for that alpha level just to kind of make note of it from the problem. Step 5 is to make our decision based on the alpha level and our p-value. We will be doing the exact same comparison to see if our p-value is smaller than our alpha value. And if that is the case, we reject our null. If not, we do not reject our null. And then we interpret the results by writing some sort of conclusion that pertains to our original problem. Okay, so I'm going to continue with that M&M problem, which is a little out of order from the notes that you may see in my class. I did a different example first, but I'm going to go and jump to that M&M problem. And we'll work it through from start to finish. So here is that M&M problem with a little bit more details because we did have to go take our sample and so forth and find out how many were brown and everything. So we're going to start with step 1 and then step 2 and all of that. So first of all, step 1 is to write our hypotheses. So the manufacturer claims that 40% of all M&Ms are brown. So, and we have already kind of set this up. So I know we're talking about a proportion. The assumed proportion is to be that 40%, that 0.4. We're going to find out if it is different. So that means not equal to. Okay, since we are talking about a proportion, step 2 is to kind of look at what n times p0 and n times 1 minus p0 is. Now, n is going to be our sample size. So they took a sample of 500. So we're going to take 500. The p0 is the p-value listed in the null hypothesis. So that's my 0.40. And then my 500 times my 1 minus 0.4, which is 500 times 0.60. This gives me 200, and this gives me 300, both which are larger than 10. So we can use our normal. So it's bigger than 10, bigger than 10. So we can go and use our normal curve. Step 3 would be to calculate that test statistic. So if I were doing it by hand, which I am not going to do, but I will put the numbers in so you can see what you could do if you were doing this one by hand. It is our p hat minus p0 all over the square root, p0, 1 minus p0 all over n. Okay, so first of all, thing I will calculate is that p hat, which is our sample proportion. So look, going into our sample and finding what the p hat is, the proportion of our sample that was brown. So they took a sample of 500 and found that 245 were brown. So my p hat is at 245 over that 500. Which I could turn into a decimal if I wanted to, which I will to make my life a little easier. And I come up with 0.49. So if I were putting all my pieces in, I'd have that 0.49 minus my p0, which is the 0.4, all over square root. My p0, notice it is p0 and not p hat because we are assuming that the null is true until we prove otherwise. And then my n is that 500. And I'm going to actually get this value from salt. But you could do it by hand. Step 4 is to find our alpha value and our p-value. The alpha value is stated in our problem. It is up in the top here. So I go and look for alpha, which is 0.05. My p-value I will get again from salt or the statistical package that you may be using. So So I'm going to go into salt right now and find it. Okay, so I'm going to share salt. Okay, so again, to do this, I'm going to be in my inferential statistics. We are not doing a one sample T because this is not a T situation. This is a proportion. So that means we're doing a one sample proportion because we did take a single sample, 500 M&Ms. And in that sample, so the first piece that happens is the sample information. So that was the 245 out of the 500 that we had. So the first piece that goes into our software, into SALT, is the sample information. Very similar to when we were doing the mean, we put our sample information in first. Then we put in that hypothesized piece, and we are assuming that it's equal to 40 versus, and in this case, the not equal to. So I have that one written up the way it should be. And then I'm going to hit my generate results. This one is written a little bit differently, mostly because there's more information and it would take a little bit longer thing. But again, they do write the hypotheses here. So I do double check to make sure that those look like the way I had them. And then it gives me my test statistic, which is that Z statistic. So it's 4.107919. And my p-value is 0.00004. I also double checked down here just to make sure. There's my N, 500, the number of successes, that 245. There's the p hat that I did calculate. Here is my standard error. So that's the square root of the pieces that I had. So just kind of be aware that the standard error is also given for you. Okay, we're going to go back to our sheet and finish this problem out. So here was our test statistic, that 4.17919, which means our sample is 4.1 standard deviations above our assumed mean or our assumed proportion of 0.4. Our alpha value was 0.05. That was given in the problem. Our p-value, which I read from SALT, is 0.00004. So step 5 is to compare that p-value to the alpha level, because if it's less than alpha, we will reject. Otherwise, we do not reject. Our p-value is quite a bit smaller, so we will reject H naught, which means, now this is where we have to write our conclusion. And again, I'm not the best writer of conclusions, but there is enough. Some people like the word significant, or there's significant evidence to show that the proportion of M&Ms that are brown is different than 40%. Okay, so we have found that there is enough evidence to show there is a different than 40% proportion of brown M&Ms. We did not prove that there is more, because that's not the way we had the arrow, the inequality. We didn't have an inequality, we had just a not equal to. So we found that there's enough evidence to show that it is not equal to that 40% or that 0.4. Okay, let's do a couple more examples. And again, I will be using SALT where possible. So we have a popular gene company that claims that 2% of all genes that it manufactures have a small sewing defect. An independent quality control company seeks to show that this defect rate is higher than that. They took 250 pairs of genes and found that 75 had small sewing defects. Is there significant evidence to show that the defect rate is higher than manufacturer claims at alpha 0.1 significance level? Okay, so we're going to start by writing our hypotheses, as we always do. We are talking about the proportion of the defect rate, which is a proportion, how many out of a so many. So P, it is status quo. The genes company says it's 0.02. The independent quality control says it is higher than that, so greater than 0.02. Step 2 is to kind of verify our conditions to make sure that we can go ahead with the analysis, and that is to look at n times p0 and n times 1 minus p0. Our n was 250. Our p0 is that 2%, that 0.02. And if I multiply those together, I get 5. Here, I'll take that 250 times 1 minus 0.02, which is 250 times 0.98, which is 245. Okay, now just so you kind of understand what these numbers represent, okay, is under this assumed truth, because we're kind of assuming, we should expect to get 5 defects. Okay, notice both this is not bigger than 10. So technically we should not keep going. But if you looked at our sample, we found 75 of those things that had small defects. So we still may want to talk to the company and say, hey, look, this is what we found. Our analysis shows we should have only found 5. We found 75. So we may want to go further and to investigate what's going on. Okay, so technically speaking, we should not go through the hypotheses, but just for practice so that you can see that we will find that 75 is quite significant because it is quite a bit larger than 5. We will go through and just for educational purposes, go through the SALT to give you more practice on seeing what should be done. So technically, we should not go any further. But we will go and find step 3 and step 4 in our SALT. So step 3 is to find that test statistic, which would be a Z. And step 4, our alpha level is 0.1, but we also get our p-value from SALT. And because they don't take that long to do, we will also do it just to practice. Okay, so into SALT we go. And our one sample proportion, because we are talking about proportions, or the number of genes that had a defect. And we found 75 out of the 250. That was our sample. Our hypothesized value is 0.02, that 2%. And we are going greater than. Okay. I'm going to generate my results. There's my hypotheses, which is the same as what I had written. My Z statistic is 31.622777. And notice it gives me a p-value that is smaller than 0.00000001. 0, 1, 4 zeros and a 1. Okay, I also looked down here, 250, successes is 75, which is actually a 30%, which is quite a bit bigger than 2%. In fact, notice my Z is 31.6. So I'm 31.6 standard deviations above that assumed value. So we're way into the tail. Some p-values, sometimes they will list a 0 here, but note that p-values are never equal to 0. They're just very, very small. They're approximately 0. So some places will do this less than a certain bottom end that they have. So it really depends on the software that you are using, what that statement will be. Okay, going back and finishing this question. So we did get our test statistic right here, our test value, our p-value. Step 5 is to kind of compare that p-value, which is smaller than 0.001, which is smaller than 0.00001, which is obviously less than 0.1, which is my alpha. We will reject. Which means that there's enough evidence. If I could have actually done this test, which I might have convinced people to run through anyway, just because our 2% is such a small number, there is enough evidence. Whoops, evidence, I forgot the word evidence. To show that the defect rate of these genes is higher than 2%. Okay, we do not know what that value is, but we could then possibly set up a confidence interval based on our sample to kind of get a feel for where that true proportion really does lie. Or we could take another sample, take a couple of samples and continue to work there. I'm going to do one more example here. And I think I'll do this one. And we have that researchers found that 80% of middle school students experience bullying. Suppose new anti-bullying policies were instituted last year at the middle school. We would like to know if these new policies have decreased the amount of bullying. So they took a sample of 100 students and found that 72% of them experienced bullying. And we want to know, were the new policies effective? All right, so we're going to start. Step 1 is to write our hypotheses. We are under the assumption that 80% of all students are bullied, so our proportion is at 0.8. Versus we're hoping these new policies will decrease the amount of bullying, so we're hoping that that number goes down. We are going to check to make sure that we can continue, or at least possibly continue. Even if we do not show, I probably might go through it anyway, but N was 100 students. Our P0 is this 0.8. So under the old assumed assumptions, we should have seen 80 students. Still have bullying. That's a lot of students. And 20 students who did not experience bullying. Under the new policies, we saw 72, which is a drop. 72% of the 100, which would have been 72 students. That is less than 80, but is it significantly less? That's where the tests come in. So we are going to then again from step 3, so we are able to go and use our normal. And we're going to get our test statistic, which isn't always something that is needed as far as writing a publication, because they will probably put the p-value in there, but the p-value comes directly from the test statistic. And for educational purposes, they usually want the pair just to make sure that you did these things correctly. But nowadays with the software, it's just easier to get at. So here we're going to get that test value from SALT. I'm also going to put my alpha value in here and get my p-value from SALT. Okay. 72, is that significantly smaller? We'll find out in a moment. All right, so we are still doing a one sample proportion. We had 100 students, 72% of them, that would mean that we had 72. You might have to actually calculate that number. I can easily do that in my head. I take 72%, which is 0.72, multiply it by my n to get the number of successes. My hypothesized is that 0.8, and we are doing less than this time. And we will generate our results. So there's my p equal to 0.8 versus the p less than 0.8. I have a z statistic of -2, such a beautiful number. And I have a p-value of 0.02275. Can double check your n, your number of successes. We got a standard error, your p-hat. There's that 72% that was stated in the problem. So you can double check to make sure you calculated your number of successes correctly. And we have all of our information. I have it all written down. So I'm going to go back to our problem. So we can finish this off. So I have a test statistic of a -2. We have that p-value of 0.02275. My alpha value is 0.01. So step 5, I forgot to write all step numbers. Okay, not that the statisticians will have step 1, step 2, step 3 all written down. They will have everything kind of organized in some manner for themselves. But step 5 is to kind of make our conclusion. So we compare the p-value. So is our p-value smaller than our alpha value? That's kind of what we ask ourselves. Is p smaller than alpha? The answer to that is no. Now, if we had chosen a different alpha, like 0.05, then yes, it would have been. So the alpha value can determine, helps determine whether or not things are going to be significant or not. So, but the smaller the alpha value, the more change, the larger the difference has to be in order for it to be significant. So this problem, though, we will not reject. Do not reject H naught. Okay, so for this boundaries that we want, because we want it to be 99% sure, so we're not going to reject. So there is not enough or insufficient to show that the new anti-bullying policies are effective. We would have liked to have seen a bigger gap, bigger change. So what this school may do is try something different, try a different anti-bullying policy, try something new, and see if that actually worked. Okay, so this is how we do hypotheses testing for proportions. Very similar to that of our mean, but different. So we're going to a different test. We go instead of a T, we use our sample test for a proportion. In both times, we will put our sample information in first to the software, and then comes the hypothesized value. But still, both of them use the same 5 steps. Step 3 is a little bit different because they will have a slightly different formula for that test statistic if we have to calculate them by hand. Luckily for us, in today's world, we have software that does a lot of that grunt work for us, so we don't have to spend a lot of times pushing buttons on our calculator. In the next video, we're going to take a look at how do we compare one sample to another. So maybe the proportion of men that do something versus the proportion of women, the proportion of people in Minnesota versus the proportion in Wisconsin, or the proportion of Democrats versus Republicans, or the proportion of the 8-ounce can versus the 17-ounce can. All sorts of things comparing 2 different situations. We can do the same with means, but in this course that I'm teaching, we do not get into that detail because it gets a little bit more complicated because we can do some things called a test retest. And we want to see, did we get faster, slower, smarter, or whatever happens to be the situation. So that's one situation. We could be comparing men to women, 2 completely different groups. So we can see a lot of different situations there. And we're just giving you an introduction to these ideas. So we are not going to have the time to go into two sample means. But we will look at that 2 sample proportion. That will be in my next video. So I hope to see you there. If not, have a fantastic day.